All right, good morning everybody. I got a few announcements to start us off. First is a reminder about ACT testing. So I have quite a bit of juniors in here. If you're not a junior and you're a senior, well, seniors they escape testing, lucky seniors. I guess that's your graduation gift from the state, right? You don't have to do any testing your senior year. Juniors, you do have ACT testing next week, Tuesday, Wednesday. You should have gotten information in the mail already regarding your testing site. Your proctors hopefully are sending emails out to you to let you know who to kind of look for that day. I think I have Colin is the only person I have at my site in here, so I'll see you next week, Colin. Let's see, what else was I going to say? Oh, your answer keys. Is everybody receiving their answer keys in the mail for them to fill out before next week? So hopefully you got them in the mail like maybe on Saturday or yesterday even. If you didn't get your answer key in the mail, be on the lookout for it today. Hopefully it'll drop today so that you can fill that out prior to coming to testing next week. So that's a big thing. You got to have that answer key all filled out and ready to go, and bring it with you next week, Tuesday. You won't be allowed in the room if it's not filled out. So we got to make sure we fill that out ahead of time. For my juniors, the first day is kind of the longer day of testing. Usually we go to like 2 or 3 o'clock in the afternoon, but the second day of testing, Wednesday, is significantly shorter. So we'll wrap up around noon on that second day. They do have strict rules for ACT testing, yes. All the teachers had to go through training for it, and then, yeah, it's pretty strict rules. You can't bring anything to work on. You can't really bring food or water into the room. Can't have cell phones. It's, yeah, pretty strict, but yeah, you make it through. They do have strict rules for any test like that. That is true. Yep. Yeah. I think it's more boring for like a proctor like me, because I have to literally just sit there and watch you take the test. I can't do anything else but sit there and kind of stare at those that are taking the test. So I think I'd rather take the test than have to give it, honestly. I feel kind of bad for myself right now, knowing what's in store for me next week, Tuesday and Wednesday. But I'll live through it. I do every year. My 10th graders that I have in here, you guys will be taking the forward test, I believe. That's what they give at 10th grade. But that isn't until later in the semester. So usually not until April or May-ish even. End of April, beginning of May, I think, is usually when the forward testing happens. So that's down the road still. Yeah, I think I was the proctor in May last year too, so yeah. All right, we do have, oh, the ACTs, I totally forgot. If you show up both days for the ACTs, my juniors, you get your choice of a final exam exemption pass. So you will be emailed a Google form to fill out. And basically, if you show up and try on your test both days, you can earn a final exam pass. So that means you get to choose one class that you don't want to take your final exam in at the end of the semester. So you'll fill out that form. There are a couple of guidelines with that. You have to maintain at least a 70% in the class to qualify, and AP courses don't count. So you have to take your AP test final exams or the actual AP test. You can't use your final exam exemption pass for any of those courses. But Algebra 2 is fair game. So if you don't want to take that Algebra 2 final at the end of the semester, make sure you're maintaining at least a 70% in here, and you technically would qualify to use your pass in the class if you wanted. All right, we have one other announcement. Cassie's going to take over here and let us know about a pop tab collection project that's going on right now. So Cassie, if you want to take it over, go ahead and do so.
Okay, so one of the projects that Student Council is doing, and you may have heard about it, is the Pop Tab project. So when you finish your pop, remember to save the top. So what is it? So all the pop tabs and the money raised goes towards the Ronald McDonald House. So that allows families to stay in the Ronald McDonald House while their child is receiving care at a local hospital. And this is very easy to participate. All you have to do is either collect pop tabs, or you can save up some spare change. You can donate it directly to the Ronald McDonald House charity, or you can donate it to your local McDonald's that is participating in this. There's either a donation box inside, or sometimes they're actually at the drive-thru. So if you want to track your donations, then you go to the student gathering page under Student Council, and there you will be able to share. And our goals is either 10 pounds or $100 raised. So we can change the goal if we go over.
All right, thank you, Cassie. Any questions with the Pop Tab project that's going on? I know I have my collection going. I've asked my family to start collecting, and I didn't realize how much like soda, we call it soda, you guys are going to hate me, instead of pop. I grew up in the soda realm area. But I didn't realize how much soda my family members actually drank. I was like, ooh, that's a lot. 10 pounds does sound like a lot, but I bet with all of us around, and if we asked your family to collect, we could probably reach that goal. Ooh, if you reach Madison and Westward, they do not call it soda anymore. I believe they call it pop. It's more popular to hear it called pop from that Madison Westward range. At least back in the day when I lived out in La Crosse, everybody called it pop versus soda. So very interesting. All right, awesome. So with that wrapping up there, are there any other questions before we start today? Taking a look at 7.03 or anything, so any major questions with that? Converting between our exponential and logarithmic equations. Okay, obviously we'll continue to practice switching between the two forms as we move throughout the rest of the unit as well, especially when we get to more of that solving piece of it all. Before we focus on the solving piece of it, we are going to focus a little bit more on just those logarithmic functions and what the graphs of them look like. So before we get too advanced in the algebra piece of it all, we are going to just halt a little bit and take a look at what the graphs are going to be for these. So today we're going to look at how we can graph logarithmic functions by hand and using our graphing calculator tools. All right, so before we get too far, inverses, what does that mean again? So when we hear that term inverses, which is going to come up a lot today, what does that term inverse mean? It is the inverse of the original operation, but what does that mean? What do we have to do before we solve for y? You're right, Sophie's got part of it there. You got to flip it. Yeah, so essentially, when we're taking inverses, that means you're flipping or switching, oopsie, your x and your y, and then solve for y, right? It's also known as reflecting over what line? Does anybody remember the line that we reflect over? Yeah. And when we reflect over that line y equals x, so it's technically y equals x. If I were to draw a coordinate plane, this is the line of reflection that we're technically doing. It does go through the origin, but it's going to be that positive slanted line there with your slope of 1. When we reflect over the line y equals x, remember your domain and range technically switch places, right, with the original function. So your inverse and the original function have opposite domain and range. And when I say opposite, I mean they flip, not opposite values. I lost my train of thought. Oh, darn. Oh, the other thing was your horizontal and vertical line test, right? Your vertical line test checks your original function to see if, or your original graph to see if it's a function. The horizontal line test you can use on the original graph to see if it's the inverse will be a function. So we also had those couple of pieces out there as well. When we talk about logarithmic functions, what's the inverse of a logarithmic function? So our main goal today is to focus on those logarithmic functions. But what's the inverse of one? Do you guys remember? Not E. Not technically E. Yeah, it does start with E though. The exponential functions. So exponential functions and logarithmic functions will be inverses of each other. And we did hear that thrown out a couple of times already in the unit, but we didn't really explore why or how those were inverses until today. So that's what we're going to focus on, is if I have an exponential function, can we use the logarithmic to find that inverse? So we'll go ahead and take a look at those. All right, so because I'm not the greatest with graphing freehand here, I decided to pull some graphs for you to look at instead. They're a little neater here. With your exponential function, so looking at my first example here, and technically you can look at both examples. The first graph here is where you have exponential growth, right? So notice that your base is larger than 1 in this blue function. And the blue function does represent your exponential function. Notice how you have 2 to the x power. Right? Over here, same thing. You do have your exponential function in blue, but it's exponential decay. Right? So your value for your base is between 0 and 1. All right, with these exponential functions, we do have asymptotes that are occurring, right? Most of the asymptotes in a kind of a basic exponential function have y equaling 0, right? So you basically have that horizontal asymptote being the x-axis. Unless you have some type of transformation occurring where it's shifting up or down, that would affect your horizontal asymptote. But most of them have a horizontal asymptote of y equaling 0, no matter what the base is, right? So you can notice if you have exponential growth or decay, you do have that horizontal asymptote occurring. Now when we take a look at the logarithmic functions in red, you can see that they are reflected over that green line, right? But instead of a horizontal asymptote occurring, what type of asymptote do you have for your logarithmic functions? Yeah, you've got vertical asymptotes occurring. So we can see that switch occurring with those inverses here as well. So instead of having horizontal asymptotes, now we've got those vertical asymptotes. And a vertical asymptote, remember, is denoted by x equaling some number. I already mentioned that the domain and range will kind of flip or switch places there between your exponential and your logarithmic function. So in an exponential function, your domain is all real numbers, right? So in an exponential domain is all reals. Your range is y is greater than 0, right? But in your your logarithmic functions, what's the domain on your logarithmic functions, and what's the range going to be on your logarithmic function? So let's start with the domain. What's the domain going to be for your logarithmic functions? Careful, domain is still representing x though, but I like that you have greater than 0. Just make sure you're still using the correct variable to represent the domain. Yeah, so it's going to be x is greater than 0. And then what will the range be for your logarithmic? Yeah, all reals. Now this will change, obviously, depending on transforming your graph left, right, up, or down, right? So sometimes we have to keep an eye out for that range in your exponential function, because that's going to affect the domain in the logarithmic function for its inverse, right? But if it is kind of that basic graph, we do have that occurring. All right. Any questions with that at all? Okay, then how do we graph a logarithmic function without a graphing calculator? We can use our knowledge of transformations to kind of help guide us on what the graph is going to look like. Or we can start creating a table of values, and then we can use our table of values to help us find distinct points on our graph. We're actually going to use both of those ideas to graph a logarithmic function by hand today. So the first thing we're going to look for, and we probably should write this down in our notes, here's kind of your basic logarithmic function. So log base b of x minus h plus k. Now h and k are transformations that are happening with your graph. How is that h value affecting your graph? Is it moving it right, left, up, down? How exactly is that h value affecting our graph, do you think? It should be moving it left or right, right? That's kind of what we knew about that value that was inside parentheses next to your x. Yep, that should move it left or right. And then what technically is k doing? Up or down. Yep, and Daria's got it exactly correct. You think opposite when you're working inside the parentheses. And then that value or constant on the outside is shifting it up or down. And it's exactly what you would think. If it's a plus or a positive number, it's shifting it up. If it's a negative number, it's shifting it down that many spaces. Okay. So the first thing we're going to do when we're graphing a logarithmic function is finding that vertical asymptote. The vertical asymptote is happening inside that parentheses at the value of x equaling h. So you're going to take whatever is inside your parentheses and basically solve for x in there. And that's going to be your vertical asymptote. So in the example down here, where is the vertical asymptote occurring? At x equaling 4. So I'm going to go ahead and just draw in the vertical asymptote at x equaling 4. All right, remember an asymptote is kind of an invisible line, right, that your graph approaches but never crosses over. So as we graph our values for this logarithmic function, we know that it's never going to cross that red line. All right, off to the side, decide what the general shape of your graph is going to look like. So we know that this is probably going to be, well, first I should ask, is this exponential growth or exponential decay that's occurring? It is going to be growth. Now, how did you know it was growth? Look at the base. What's the number of the base in our logarithmic function? 3. Yeah, that's a big piece. Now, you're probably wondering why we can't go on the calculator and graph this. What base does our calculator work in? 10. Yep, so if it's not base 10, our calculator isn't going to graph it nicely, right? We can use the change of base formula, which is what we have to do in order to graph it on the calculator, but it's a little bit cumbersome, right? So we do check out the base. It's 3, which means it's larger than 1, so your graph should be growing over time, right? So I believe if we look back here, this is your exponential growth example here. Your base is greater than 1. We know the graph is going to take on this type of shape somewhat now. If it's taking on this sort of shape, do you think it's going to appear on the right-hand side or the left-hand side of my vertical asymptote? Yeah, it's going to be happening on the right-hand side somewhere. So we know, I'm just going to kind of come up above this and just do a rough sketch. We know it's going to look like that somewhat, and it's going to appear on the right-hand side of that vertical asymptote. All right, now we're going to actually plot a few points, and we'll make our rough sketch. Now, what values for x do you want to choose here? Make sure you're doing this wisely. Yeah, now why did you choose 5, 6, and 7 to start off with, Daria? Exactly. Your x values can't be lower than 4, right? We know that that graph cannot cross that red line at x equals 4. So you cannot choose x values 4 or less, right? So starting at 5 is a really good choice there. If you want to do 5, 6, 7, that's fine. I'm going to space mine out just a little bit so that I can kind of get a better representation of maybe where my curve is going to happen. So to do this, we are going to have to okay. Whew, I lost internet connection. I think I'm back. That like never happens to me, so I don't know. Bad timing, I guess. But I'm back here. All of a sudden, I'm like, uh-oh, my audio is frozen. My face is frozen. That's never good. All right. So the first thing I'm going to do, because I don't know when I actually lost connection, so the first thing we're going to do is just substitute it into our logarithmic function over here, the values for x that we've chosen, and simplify that little piece inside parentheses first. So you probably can do this in your head, hopefully. Right, log base 3, and here's where all the fun emoticons usually happen. And now, instead of f of x, we're going to replace that with our y. We're going to want to go ahead and put this into exponential form. So I think at one time I saw Sophie typing when I couldn't respond. Put it into exponential. Yeah, 3 to the y equals 1. What will that y value be so that we can have it equal 1? So what does that exponent got to be? It's got to be a 0, right? So the first point on our graph is 5, 0. Awesome. All right, the next thing we're going to do is we're going to try that with the 8 as well. So log base 3, 8 minus 4. is a 4, and maybe I should try some nicer numbers. Instead of 8, let's try a 1 or a 7. I'm going to adjust this. You can get decimal answers here. That's totally fine, but I'm going to tweak it so that it actually works out in our favor and we get whole numbers for our values. So if I make that a 7, I can work in multiples of 6. Yeah, so 3 to what power equals 3? 3 to the first power. Yeah, so y would equal 1. So if I can kind of keep my parentheses, inside my parentheses here, multiples of 3, it'll work nicer for us when we try to figure out what that exponent's going to be. So the next point is going to be at 7, 1. Let's see, the next multiple of 3 I can think of, so we did 3, 6, 9. If I want an answer of 9 in here, technically we got to start with x being 13, right? Because 13 minus 4 is going to be a 9. Does that make sense to everybody if we let x equal 13? And I think I skipped 6. So if we go with 6, that might work as well. Although 3, you can't really get it at power. I think this will be good. I don't think 6 would technically work. 27 would, though. We'd want 27 because we're doing our powers of 3, it looks like. Yeah, so 2. We notice that this is not growing as fast, though, right? 13.2 is up here somewhere. So we can, using those couple of points, we can kind of generalize what that graph is going to look like, because we know it curves, but it's not going to be like a drastic increase, right? Not like those exponential functions we saw. So we can do this one by hand by choosing our x values wisely based off of our base of 3. So if we can kind of tweak it and work it in our favor, where what's inside the parentheses will be a power of 3 somehow, that's going to work nicely for us. So that's why we chose these certain values for x. All right, can you do this on the calculator though? So is there a way to type this on the calculator? There is, but you must use your change of base formula to create the graph on the calculator. All right, so what was our change of base formula that we saw in Monday's class? Does anybody remember? Yeah, your log, and we don't want to use 9. We want to actually keep it our x minus 4, right? Because that's what we have in the original function here. So we got to do log, technically y equals, log of x minus 4. Yeah, for that specific one, that's what it would be, divided by log of your base. So your base is always in that denominator. Yep, so whatever the base is, it's log of the base there. Now we do want to probably put parentheses around the logs there. Maybe not, because we're not like adding or subtracting outside of it, so it might work without any parentheses being needed here. But if we type it in like this, we should be able to get that graph. Now, I'm going to see, I would probably recommend using GeoGebra if you don't have your own graphing calculator handy. I think that's the easiest tool for you to use there. I'm going to see if the calculator in here is going to do it. It will. Yay. Okay, so using my change of base formula, there is that graph, and you can see that they have that vertical asymptote at x equaling 4. Notice the graph does not cross over this invisible asymptote here at x equaling 4. It gets really close to it. In fact, it's so close to it, it looks like it's ending right in here. And you can't see my cursor, so one second. See if I can do a screenshot real fast for you so you can see where I'm pointing at. So it almost looks like it stops right here, but it doesn't. It does keep going in this direction, but it's getting so close to that vertical asymptote that it can't technically really graph it anymore without it looking like it's touching it. So that's why it looks like the graph kind of abruptly ends, but it doesn't. It will keep going forever in that direction. It's just that the program can't handle like drawing the thickness of the line anymore because it's getting so close to that value of 4. So if it were to keep going, the thickness of the line would make it look like it's going to cross it over it, but it won't. It's getting very, very close, and some of the values are getting so close that it's like 4.000000000, and then a number, right? So depending on how close you get there, it gets extremely close to that value of 4. Exactly, but it never will touch it, and it never will cross over it. That's why we can state that the domain is going to be for this one. So domain is x is greater than 4. And then the range is all real numbers, technically, right? Because it does keep going in this negative direction, and it is increasing very slowly, but it does increase upward still. It doesn't really have a cap. We'll talk about caps at the upper ends when we get to our population, logistic population growth, because there is a special type of logarithmic function that does have a cap on the upper end, but we haven't reached that quite yet. Right? So technically the range is all real numbers for these. Okay. There's a lot of information to take in there. Any questions with how we either graphed it by hand or how we use the change of base formula to graph that in our graphing program? All right, let's just talk about it because I want to at least tackle a little bit of your assignment with you here today. I know I don't usually get to do that, so if we can tackle some of that written assignment, I'll help you out there. Taking a look at our function here, what type of transformations do we have occurring? So let's just talk about the transformations that would occur in this graph. What are you guys noticing? This is not your assignment yet. So this is just a practice one still. We're moving to the left 3. Left 3, down 5, reflection. Any idea what the reflection is going to be over? It's a 50-50 chance, x or y axis. Yeah, it's the x-axis. If it's in front of the entire function, it's your x-axis. If you see the negative sign happening inside of your parentheses that's attached to the x variable only, that's a reflection of the y. All right, so if it's happening out in front of the entire function, we know that that's going to reflect over the x-axis. Now, is this exponential growth or exponential decay, do you think, based off the base originally? Yeah, the base is 1/2, so you're thinking decay. That reflection over the x-axis might tweak it a little bit. We'll see when we actually get to graph it there. So because those reflections can somewhat throw things for a loop, if the reflection wasn't there, we would definitely expect a decay to be occurring because the base is between 0 and 1. Let's go ahead and see if I can actually graph this using a graphing program. This is a little bit more tricky. To do this one by hand, we'd have to, and we might actually have to do this by hand. I'm not sure if we can actually type all of that in to a graphing program or not. First, we got to start with the vertical asymptote. Where is the vertical asymptote occurring at? X equaling -3. Okay. So start with that vertical asymptote. Again, we use what's inside parentheses here to help us with that. Picking values for X, I believe this is going to be occurring on the right-hand side of our graph again. Let me go back 2 slides to take a look. Yeah, so generally this is what we would think for exponential decay. And it almost looks very similar to it with the reflection for the logarithm there. But with the reflection piece of it, I'm thinking our graph might look something like that because of the reflection. Originally it was supposed to look like that. But because of the reflection piece occurring over the x-axis, I'm thinking it might take on this shape a little bit more. Yeah, I would try -2. Yep. My first value for x, I would try -2 and simplifying that in. So -2 plus 3 is a 1. Using the change of base formula, we got to be careful here. The change of base formula is only occurring for this little piece of it. All right, so that helps my memory now for how we would type this into our calculator. So the change of base formula, we have to, or changing that to exponential, basically you're asking yourself 1/2 to what power equals 1. So 1/2 to what power equals 1. That's 0, right? So technically we'd be doing -0 and then -5. So we're only really simplifying or changing this piece in yellow here to the exponential to simplify it, and then we will just bring down the negative sign for that yellow piece and then the -5. So it looks like -5 is what that's going to simplify to in the end, right? So -2, -5, all the way down here. Right, 0 technically can't be negative, so you would just ignore it with that first one. But later as we choose more points, like when I do -1, and we want to try to simplify that, we've got to remember that that's still in there. So if I use a -1, technically inside parentheses here, I'd be looking at a 2, right? So I'm thinking negative log of 1/2 of 2 minus 5. So in the yellow here, we're going to change that to exponential. So you're asking yourself 1/2 to what power equals 2? Can we do this one mentally? If not, you can use your change of base formula, log of 2 divided by log of 1/2. But yeah, that is going to be a -1. So technically a -1 is, yep, a +1 minus 5 is going to give you a -4 for that value when you simplify. So we can see it's going up a little bit here. If I choose one more value for you to test out, like if I just say x is 1, let's go ahead and see what happens there. So negative log of 1/2, that's a 4 this time. Inside here, you can use change of base to help you simplify that, or you can change it to exponential. So 1/2 to what power equals 4. It would technically be a -2 in there, right? Once we start thinking of that, it should be a -2. So minus -2 minus 5. So that's a 2 minus 5, which is a negative 3. So we can definitely see the graph is starting to increase a bit there, which is what we expected, right? With that reflection, we originally thought we had it like this, but it would be reflected over the x-axis. So we did think it was going to take on this shape. All right, now entering this into your graphing calculator, we're going to go ahead and do y equals negative, and then we have to do log of x plus 3 divided by log of 1/2. And then once you have that, you want to make sure you have your minus 5 on the outside. So kind of the negative will be in front of everything, and the minus 5 is on the outside of it all. So we may have to put parentheses around all of that for the change of base formula happening in this area right in here. Okay, so we'll put parentheses around that for the change of base formula occurring. And then we can graph that in GeoGebra to see the true graph there. So that's a little bit trickier. Let me see if I can actually get that accurately graphed here. Yeah, whew, I got it to work, first time. If I zoom out a little bit, we can see that vertical asymptote at x equaling negative 3, and it is taking on that same shape that we had sketched on our board there. Phew. Notice though in the equation for the y equals in blue there, how I put parentheses around the whole change of base. It might, because we did shift things around. So if you have shifting up or down, it may cross that x-axis, yes. So this one does in fact cross the x-axis. It takes a while to do that though, all the way out here. And this one does cross the y-axis as well, only because we shifted it left 3 spaces. If you shift something left, that's when it's going to cross your y-axis. All right, lots of stuff going on there. Any questions with that, or how you would enter that one or those type of pieces into your graphing calculator to check things out, or see that graph a little bit more cleanly sketched there? So any questions with that at all? So the change of base formula is going to become kind of your best friend a little bit with some of these transformations and being able to simplify along the way. So you're going to find yourself using the change of base formula a lot when you have to sketch a graph by hand. Okay, your homework assignment is talking about like the pH levels in pools, and they do give you a function to kind of follow here for your pH levels. So the first thing they're going to ask you to do, because they give you a bunch of information there, it says create a graph of the pH function either by hand or using technology. All right, I have a feeling that most of you are probably going to use technology to create your graphs for the homework, and that's totally fine. So if you're going to go ahead and do that, remember you're going to have to use your change of base formula if the base is not your common base. If you want to do by hand, that's totally fine. You look out here because what's the base in the function that they give you? 10. Yeah, so you technically look out here, and for part 1, if you were to graph this by hand, first of all, GeoGebra only works with x and y. So you're going to just have to type in y equals negative log of x. Yeah, and you don't have to worry about your change of base formula because it's in base 10, and that's what your calculator works in. So we really lucked out with the homework assignment because it's in base 10, and we do not have to worry about the change of base formula in order to graph it in GeoGebra. All right, so when you get that graph, technically you're looking for where the pH is 0 and where it is 1. So you're looking when y equals 0, what will x equal? And when y equals 1, what will x equal? So that's what you're searching for in question 1. All right, any questions with question 1 and what that first piece is asking you to find there? You can find the values for x by using substitution or your graph. So if you want to try to work backwards and use exponential form to find those, go for it. Otherwise, you can just use your graph in GeoGebra as well. Not in place of x, in place of y. So you're substituting 0 and 1 in place of y. And you're kind of working backwards to solve for x then. Yeah, so it's a little bit different than kind of what our substitution has been in the past, right? So let's keep an eye on that. Yes, yep. I think. I have to go back and look. 10 to the y, I believe. Something like that. I don't know. You'll have to look at your exponential form to figure that one out. I want to make sure we get back to the second question here to talk about the negative sign. It says the pool maintenance man forgot to bring his logarithmic charts and he needs to raise the amount of ions in the pool to 0.5. So to do this, he can use the graph you created in part 1. Use your graph to find the pH level if the amount of hydronium ions is raised to 0.5. Then convert the logarithmic function to an exponential function. So for that one, they want you to use 0.5 for t. So technically you're looking at y equals negative log of 0.5. Yes, t is your x value that you had to substitute in, right? Now, because you have a negative in here and you need to change this to exponential, I would technically divide both sides by the negative sign before you write this in your exponential form, right? Because you weren't sure how that negative is going to play into the exponential form if it stays in this format. But if you divide both sides by that negative sign, it should become more clear how you can change that to exponential form then and where the negative sign is going to have to fall into place. All right, so technically the only thing left you need to do for question 2 is put that into exponential form. Exactly. Yep. So I gave you a huge hint there that the only thing left to do is put that in exponential form. All right, part 3. You definitely can. You're taking a look at your transformations. So there's 3 different transformations that they give you, and they're asking you to look at each one separately. It says the pool company developed new chemicals using the pH function which they gave you. Explain which transformation results in a y-intercept. So the normal graph that you are going to get in part 1 is not going to have a y-intercept. In fact, I don't know if it's a decay or growth. I think it might be a decay because of the reflection piece of it. But originally, it's not going to cross that y-axis, right? So you have to look at the transformations that they're giving you in these 3 parts. You have to explain what is the transformation that's occurring and which one of these transformations or which ones are going to result in your graph crossing the y-axis. So all of a sudden you'll see it crossing over this yellow line. So the first thing you have to do is tell me the transformation and then will it cross the y-axis. So this first one, what transformation is happening in the first setup here? So you have your function plus 1. What type of transformation is occurring? Up 1. If you're just shifting your graph up 1, will it cross the y-axis then? No. Nope. All right, so that's what you're looking for the last two pieces as well. So we kind of did that first one together. The transformation is up 1. This will not cross the y-axis as you're just shifting everything up 1 unit. So that is not going to affect the y-intercept at all. So that's what you're kind of looking for the last two pieces. One of those will affect it, one of them will not. So heads up with that. You do not need to graph it. You can if you'd like to help with your explanations or verifications, but technically the graphs are not needed in part 3 here. If you want to graph them just to show, you can, but technically they're not needed. All right, any questions with that homework assignment? So it's only 3 questions long. I gave you a really good head start on it there. Okay, I know some of you got class at 10 and I've got office hours starting here, so I'll let you go. I did put the PowerPoint, I opened it back up, so if you need to go back to any of the slides to copy things down, you can do so now. Otherwise, you guys are free to leave. Have a great day. Yep, and I'll see you guys next week, Monday. Bye, everyone.